Hello, thank you for watching. I hope you guys are doing well. So I want to tell you about a new construction that starts with a toric surface. We blow up one point and we end up with a surface which has a complicated effective cone of divisors. So this in turn has applications to the birational geometry of other higher dimensional varieties, among them some moduli spaces of stable rational curves. This is based on joint work with Antonio Laface, Eugenia Tevelev, and Luca Ugalia. So I would like to start with the application. So I would like to recall a few facts about moduli spaces of stable rational curves. I will always work over an algebraically closed field of arbitrary characteristic. And so what I call the configuration space M0n is the set of n distinct points, labeled points on P1, taken up to automorphisms. So I identify two n tuples if there is an element of PGL2, an automorphism of P1, that takes the first point to the first point, second point, and so on. If n is equal to 3, this is just a point, because we can identify the 3 points with 0, 1, and infinity using an element of PGL2. In fact, in general, for any n bigger or equal than 4, we can identify 3 of the points with 0, 1, and infinity using an element of PGL2. And then the data that is left is just n minus 3 more points other than 0, 1, and infinity, and different points different from each other. So when n is equal to 4, this is just P1 without 0, 1, and infinity. And it is not hard to show that if you take the P1 trivial bundle over this with a constant section 0, 1, and infinity, and one more section given by the diagonal corresponding to the fourth point, this is a universal family for our moduli problem, in the sense that any family of projective lines with 4 sections which are mutually disjoint will be a pullback from this one. So now this is a non-compact algebraic curve, which we can compactify to P1 in a canonical way. We can think of the points that we added here simply as the fourth point coinciding with one of the other 3. But we could also, instead of just allowing 2 points to coincide, we could just insert a P1 and move the 2 points that were coinciding as distinct points on this new P1. So we obtain another meaning for the points that we added. And so this turns out to be also a functorial compactification. For any n, in fact, there is a functorial compactification that generalizes this one. So M0 n bar is the Deligne-Mumford-Knudsen compactification, which is a fine moduli space for the functor of stable rational pointed curves. So a pointed rational stable curve consists of a tree of projective lines. So a curve with arithmetic genus 0 at worst nodal, and with smooth distinct points on it, such that the log canonical line bundle, so the dualizing sheaf of the nodal curve twisted by the points, is ample. So we have a positive degree on every component. And to recall, if you have the dualizing sheaf of a nodal curve, this is, if you restrict to a component of the curve, you obtain the canonical line bundle of this component, twisted by the nodes which lie on this component. So if the component is a P1, then you get O minus 2 twisted by the nodes. So the condition is a combinatorial one. We need to have at least 3 special points on every P1, where special means either a marking or a node. So M0 n bar is a smooth projective scheme over spec Z, which represents this moduli problem. And so from now on, I always base change to an algebraically closed field, and I'll consider M0 n bar as a smooth projective variety over our base field. And so what we did is compactify the configuration space by adding reducible curves. So more precisely, what we added is some codimension 1 subvarieties, which we call boundary divisors. So generically, these come from curves with 2 components and with markings from, the markings will partition into some markings from the set I on one component and the complement on the other. Each set should have at least 2 points for this to be stable. And so we take this, this locus and we close it up. Yeah, so we add their further reducible curves, which correspond to the generations of these ones. So when n is equal to 5, there are just exactly 10 boundary divisors. And so these may intersect, and the intersection points correspond to curves with 3 components for n equal 5. So what kind of variety did we create? So there is a theorem of Kapranov that describes M0 bar as an iterated blowup of a projective space. So you start with Pn minus 3. You choose n minus 1 points in a linearly general position, which you can fix up to the automorphisms of Pn minus 3. We blow these points up. Then we consider the lines spanned by any 2 of the points, take their proper transforms, blow them up, take planes spanned by any 3 of the points, proper transforms, blow up. And we do this for all the linear subspaces spanned by these points, so up to codimension 2 linear subspaces. This construction depends on a choice of a marking. So for every marking, we have a map from M0 bar to Pn minus 3, which is such an iterated blowup. So for n equal to 5, this describes M05 as a blowup of P2 at 4 points. So it is a Del Pezzo surface of degree 5. It's a Fano surface with the anti-canonical line bundle being ample. When n is equal to 6, you can prove that M06 bar is the desingularization of the Segre cubic, a minimal desingularization of the Segre cubic at its 10 nodes. So the Segre cubic is the unique cubic hypersurface that in P4 that has 10 nodes. So in this case, the anti-canonical line bundle is not ample, but it's big enough. And as n grows, the positivity of minus k disappears. So for n bigger or equal than 8, for example, the anti-canonical line bundle is not even pseudo-effective. So no multiple of it is effective. So what we have in the end is a rational variety, which becomes further and further away from being Fano as n grows. And also the Picard number grows exponentially in n. But nevertheless, we are interested in the birational geometry of this space. So we would like to understand its fibrations, or more generally, its maps. And so this is to say we're interested in effective divisors. So just to set up some terminology, for every normal projective variety X, if you look at the Néron-Severi group of line bundles, Cartier divisors up to numerical equivalence, so 2 Cartier divisors are equivalent if and only if they intersect curves in the same way. If we consider the corresponding vector space, real vector space, if we look at effective Cartier divisors and their classes, we consider the cone generated by them and close this up in this vector space. This is what's called the pseudo-effective cone of divisors of X. I'll call this simply the effective cone. And in general, if you have a cone in a vector space, a one-dimensional ray of this cone is called extremo if it has the property that whenever we write an element on it as a sum of 2 elements in the cone, these 2 elements need to belong to that ray. So it can be like in this picture that, that the cone is polyhedral in the neighborhood of this extreme array, but this does not need to be the case, for example, here. So coming back to the effective cone of M0 M bar, so every boundary divisor can be seen to be contracted by a Kapranov map, one of the n maps that we have. So this is now a birational morphism between smooth projective varieties, and every exceptional divisor for such a map will generate an extreme array of the effective cone. So for example, in this way, we see that every boundary divisor on M05 bar is in fact a -1 curve. And so there are exactly 10 boundary divisors and 10 -1 curves on a del Pezzo of degree 5. So these are exactly the same. And now, like for any Fano surface, any del Pezzo surface, the effective cone is generated by -1 curves. When n is 6, it is not true anymore that the boundary divisors generate the effective cone. So there is a new type of divisor that appears here, the Kiel-Vermeer divisor. These were independently discovered by Kiel and Vermeer. These are divisors which intersect the interior of the moduli space, so the configuration space M06. It turns out, however, that the Kiel-Vermeer divisors, together with the boundary divisors, do generate the effective cone. This is a result of Hassett and Schinkel. It should be noted that there are 15 Kiel-Vermeer divisors, but up to the S6 symmetry, there is just one. So the picture is relatively simple. However, when n is larger than 6, we can generalize this construction of Kiel and Vermeer. So with Genia Tevele, we constructed something we called a hypertree divisor. And these are also divisors that can be, are exceptional divisors for a birational contraction, not quite a morphism, but a birational contraction. And so the same is true here, that an exceptional divisor for such a map has to generate an extreme array of the effective cone. And here, as n grows, even up to symmetry, to the SN symmetry, you still get many, many new divisors. Finitely many, but many. And in fact, this is not everything. So for n starting with 7, there are other constructions of extremal divisors. So due to OP and Doranjan, Siracusa, Jensen, which construct so other extremal divisors which are not of hypertree type. So this complexity is now explained by our theorem. So the theorem says that the effective cone of M0 M bar is in fact not polyhedral when n is at least 10. And this is true in characteristic 0 and in characteristic P for an infinite set of primes P of positive density. And this will include all the primes up to 2000. So just to clarify, when I say a polyhedral cone, this just means you have a finitely generated cone, and a non-polyhedral cone is something that's not finitely generated. Yeah, so it can be that the cone has some round parts. It can be that it is locally polyhedral but has infinitely many extreme arrays. And I will also talk about rational polyhedral cone. This just means that it's a finitely generated cone generated by the elements of the lattice that defines the vector space. In our case, the Neron-Severi group. Okay, and so to connect to the two-dimensional picture, yes, because in the end, the result I'll talk about is about surfaces. We need what we call a rational contraction. So I will call a rational contraction a rational map between two Q factorial normal projective varieties. So a map that can be decomposed into a sequence of either small modifications or surjective morphisms. So here, a small modification is a rational map, which is an isomorphism on big open sets. So big open set here just means that the complement has codimension at least 2. And so such maps, rational contractions have some nice properties. So for example, certain properties are preserved by them. So for example, the property of being a Mori-Dream space, or the property of having a polyhedral or rational polyhedral effective cone of divisors. So let me start with the second property. So if you take a small modification, then the two effective cones are actually the same. This is because if you take a divisor, you intersect with this big open set, you can take its image. For a surjective morphism, it's not immediately clear that if you take the effective cone and its image, like the push forward map, then this is you end up with the effective cone. So the image equals the effective cone. So here you have to use a theorem of Buxom, Demailly, Paun, and Peternel, which says that the effective cone of divisor is dual to the cone of movable curves. So the result is over the complex numbers, but it holds in arbitrary characteristic. The other property I mentioned here is the property of being a monodream space. So this is a condition that guarantees that the minimal model program works on this variety in an ideal way. So in particular, every Neff divisor is semi-ample. So a multiple is base point free, corresponds to an actual morphism. And another property is that the effective cone has to be polyhedral. So this notion was introduced by Kiel and Hu. And so it's essentially by definition that a small modification will preserve the property of being a monodream space. And then for surjective morphisms, this is a theorem of Okawa that the property is preserved. And as examples of monodream spaces, a prime example here, after which the definition is essentially modeled, is toric varieties. And then more generally by the theorem of Birkar, Karshini, Haken, and McKernan, over the complex numbers, every Fano variety or every variety of Fano type is a monodream space. And so there was this belief about M0 M bar that it should behave like a toric variety. This is attributed to Fulton. So this was based in part on the fact that we have this stratification into these rational open sets which resemble the torus invariant strata of a toric variety. So you can ask, is it true perhaps like for a toric variety that the numerical class of every effective cycle is a sum of classes of strata? So as we already saw, this is not true for divisors already, but still there was this belief that perhaps if you add just some other simple cycles there, perhaps this is still true. Perhaps it's still true that this is a monodream space. So we have something similar to a toric variety. So this happens not to be true, but instead the better analog is a blown-up toric variety. So it's if you want, if you are looking at a new class of varieties, take a toric variety and you blow up one point, and we want to choose a general point. And so this is you're one step away from toric varieties, but this becomes already, the birational geometry will become already very complicated, as I'm about to explain. So for example, for M0 M bar, you can prove that M0 M bar is similar to the blow-up of a particular toric variety, namely the Losev-Manin moduli space. And we blow up the identity point of the open torus. So there is a way to squeeze M0 M bar in between two rational contractions. One is to the blow up of a toric variety of the same dimension. This is just a blow up map. And then the other one is you take the Losev-Manin space of dimension one higher, and there is a rational contraction from its blow up into M0 M bar. This is a result with Julien Tevele from 2015. So the Losev-Manin moduli space, you can think of it in two ways. You have a blow-up description, like the Kapranov description of M0 M bar. So this is the exact same description, except you have 1 point less. So you start with a projective space of dimension -3, you blow up n-2 points in linearly general position. You can fix these to be the points where just one coordinate is non-zero, so the torus invariant points of Pn-3. Then you consider again all lines spanned by the points, all planes, all linear subspaces, and you blow up their proper transforms. So you can see in this way you obtain a toric variety. At every step you blow up a torus invariant strata. Another way to think about the loss of money moduli space is as a functorial compactification of the configuration space. So it's in fact a particular case of a Hassett moduli space. So all Hassett moduli spaces are functorial compactifications of the configuration space. We just fix some rational weights, some positive numbers between 0 and 1, rational, and we modify the definition of our stable, what it means to have a stable pointed curve by just requiring that the log canonical line bundle with the weights thrown in is still ample. We also allow the points to coincide if the weights of the sum up to at most 1. So this changes the kind of curves you allow in the compactification. Yeah, so for example, for the Losse-Manin space, the weights are, there are 2 weights of 1 and then some weights given by some arbitrarily small positive rational number. And so with respect to these weights, the stable curves are just chains of projective lines with the points with weight 1 at the ends. So what happens is that you have a blow-up map from M0 M bar to the Losse-Manin space. So you, in fact, you blow down some of the, you contract some of the boundary divisors, which correspond now to unstable curves. And so the Losse-Manin moduli space is a universal toric variety in the following sense, that if you start with any projective Q factorial toric variety, there will be an n sufficiently large such that there exists a toric rational contraction from the Losse-Manin moduli space of dimension n-3 into this X. And furthermore, one can extend this to a rational contraction between the corresponding blowups. So we blow up always the identity point. So the reason for this is that the fan of the Losse-Manin moduli space is very symmetric. So when we look at the rays of this fan, there is we can project from these rays to a lattice of the same dimension as the X. And then the images of the rays of the fan of the Losse-Manin will cover a large area, yes, which will include the rays of the fan of X. And then you can start from the bottom up, from this refinement of the fan of X, and then construct one dimension at a time a sequence of rational contractions until you arrive back to a toric variety which has the same rays as Losse-Manin space. So it's a small modification of that. So as an application of this theorem, so this is how with Zhenya we proved that that M0 M bar is not a Morey-Drive space in characteristic 0 when n is sufficiently large. So this is because there is a rational contraction from M0 M bar to the blow up of a weighted projective plane, so a toric surface in particular, with weights carefully chosen. So this is an example of Goto, Nishida, and Watanabe that shows that that there is a choice of weights A, B, and C such that in characteristic 0, this blow-up surface has an F but not semi-ample divisor. So in particular, it's not a Morey-Drive surface. And now this argument does not work in characteristic P because in this example, what you have is a surface, this blow-up of the weighted projective plane. It's a surface of Picard number 2 with 2 negative curves. The surface is defined over spec Z. And so when when we work modulo P, then you have a surface which is defined over Fp, and now by Artin's contractibility criterion, you can always find a morphism that contracts exactly one of these curves. So the Neff cone, the two rays of the Neff cone are actually semi-ample. So now our theorem is that there exist projective toric surfaces given by what we call good polygons, such that the effective cone of the blow-up of this toric surface at the identity point is not polyhedral in characteristic 0. And for some of these toric surfaces, the effective cone is not polyhedral in characteristic P for an infinite set of primes P of positive density. And as a corollary, then you obtain that M0 M bar is not a Mortonian space in characteristic 0 and in characteristic P for, again, an infinite set of primes of positive density if n is at least 10. So here is an example of a good polygon. And this is now the polygon that allows us to construct a rational contraction from M0 10 bar to the blow up of the corresponding toric surface at the identity point. So what you have in this picture in red is the vertices of the normal fan of the good polygon delta. And in black is a certain projection of the rays of the normal fan of the Losseb-Manin space of dimension 7. And so the red dots are a subset of the black dots. And so this is what allows us to construct a rational contraction between the blow up of the Losseb-Manin space, dimension 7, to this blown up toric surface. So a good polygon will correspond to what we call an elliptic pair. And so it will be an elliptic pair of a special type where you have here a surface that is obtained as a blow up of a toric surface. So in general, an elliptic pair will consist of a projective rational surface X with log terminal singularities and an arithmetic genus 1 curve C with self-intersection 0, such that this curve is also disjoint from the singularities of the surface. In general, our surfaces that we consider will be actually singular. So now by adjunction, you have that also K times C is 0. So C squared and K times C are both 0. And we're going to look at the orthogonal complement of the curve C in the divides a class group of X. This contains C because C squared is equal to 0. And we're going to consider the restriction map from C perp into the group of line bundles of degree 0 on C. So we take a divisor that is intersects C in 0, and we take its restriction to C. Yeah, this is then a line bundle, since C is contained in the smooth locus. It's a line bundle of degree 0 because D times C is 0. And we're going to call the order of the elliptic pair the order of the restriction of C to itself as an element in peak 0. So a standard argument with some short exact sequences involving multiples of C will give you that the order is in fact the smallest integer, positive integer E, such that the space of sections of E times C is at least 2-dimensional. So if there is no such integer, so if all the multiples have exactly one section, then the order is infinite. And so if the order is finite, again, it's easy to prove that, this linear system is in fact 1-dimensional. Now, if X and C are defined over a finite field, then the order will always be finite. And so summing up, if you have an elliptic pair of finite order, then you have a pencil, a map to P1, which is the general fiber here is an elliptic curve. C is a multiple fiber. And if the order is infinite, then in fact, the curve C is rigid, so no multiple moves. And in this case, the effective cone is not polyhedral if the Picard number of X is at least 3. So this last observation is the only one that requires an argument. This is an observation that's due to Nikulin, that when you have a Picard number that's at least 3, if you consider the curves with a positive self-intersection, this is a round cone, and by Riemann, this will be contained in the cone of effective divisors. So if the effective cone divisor is polyhedral, then the only way a ray lying on the boundary of this round cone, so corresponding to a curve with self-intersection 0, the only way we can have this is if this curve is contained in the interior of a facet. Yeah, so we can write a multiple of this curve as a combination of some negative curves. So in particular, multiple moves. Yeah, so if the curve is rigid, then the effective cone cannot be polyhedral if the Picard number is at least 3. And so now, coming back to toric surfaces, if we start with a lattice polygon in the plane, we consider the toric surface associated to it. So this comes with a polarization, an ample line bundle, which I'll call L delta. I will set X to be the blowup of this toric surface at the identity point. This surface is defined over Z. I'm going to fix an integer M. And so I'll call a lattice polygon to be good if it has at least 4 vertices, and in the linear system of this L delta, there is a curve with multiplicity M at the identity point. E is the exceptional divisor corresponding to this point. So such that this curve is irreducible, and it gives us an elliptic pair of infinite order. So here, yes, I want to say that yes, of the at least 4 vertices, because we want the Picard number to be at least 3. And then the condition becomes very explicit of having an elliptic pair. So yeah, so this is a rational surface, and it has toric singularities. So it has log terminal singularities. And the fact that the curve is contained in the smooth locus comes down to the fact that the Newton polygon of C coincides with our polygon delta. Yeah, the curve is cut by an equation which corresponds to monomials corresponding to lattice points inside delta. And so the fact that the Newton polygon is exactly delta means exactly that the curve does not pass through the torus invariant points of the surface, which are the only points where the surface may be singular. The self-intersection being 0 is equivalent to the self-intersection of L delta being M squared. So this is what we call the volume of delta. It is actually twice the area of the polygon delta. And then a small calculation shows you that, that the arithmetic genus of this curve being 1, since we already assume C squared is equal to 0, comes down to exactly the condition that there are M lattice points on the boundary, on the edges of this polygon. And then we impose that this is an elliptic pair of infinite order. So C restricted to C is not a torsion element in peak 0 of C. So in the Mordell-Weil group of Q points of this curve. And here is an example. So here the integer M is 6. We have a 6 gon with 6 lattice points on the edges. Yeah, so each edge here has lattice length 1. The area is 18, so the volume is 36. And then when we look at the linear system corresponding to the polarization, L delta, yeah, so this is given by the sections here correspond to monomials in X and Y, corresponding to the lattice points. And so this linear system contains a unique curve with multiplicity 6 at the identity point. It's a magma calculation to show that this is its equation. And the terms in red are the ones corresponding to the vertices of this polygon. And this is a smooth elliptic curve with a minimal Weierstrass equation given by this equation. And the Mordell-Weil group of Q points is, here we fix the point at infinity as our origin. And so this is, the Mordell-Weil group is Z times Z with these generators, these points. And then a calculation shows that the restriction of C to itself is minus the point Q. So in particular, it is not torsion. So this is a good polygon. So the calculation here is a calculation that involves, we have to express the class of the curve C on our surface. And this is, we have to write down a combination of the torus invariant divisors on this toric surface together with the exceptional divisor, and then restrict to the curve and do a calculation on the curve. Yeah, so many of these calculations are done by magma. And so how about if we consider an elliptic pair of finite order? Can we decide polyhedrality in this case? Yeah, so we'll have to do this if you are interested in the characteristic P situation. And so we won't be able to decide it as easily, but rather we'll have to talk about a different kind of elliptic pair, what we call a minimal elliptic pair. So in general, for any elliptic pair, we call the pair to be minimal if there are no smooth rational curves that E, such that this E intersects C in 0, and it intersects the canonical class negatively. Equivalently, there are no curves E on X that intersects K plus C and negatively. So the condition of being minimal is the condition that K plus C is a Neff divisor. So to see this equivalence, one has to observe that under our assumptions, K plus C is an effective divisor. So from this standard exact sequence, the fact that you have a rational surface, this gives you that K plus C has actually exactly one section. And then also note that by adjunction, K plus C intersects C in 0. C is an F class because C squared is 0 and C is an irreducible curve. So now any curve that intersects K plus C negatively has to be a component of K plus C. Therefore, C will have to intersect any such component in 0, and therefore K times this curve has to be negative. And so summing up, an elliptic pair is minimal if K plus C is Neff. And now it's a consequence of the Hodge index theorem that K plus C is Neff if and only if K is actually a multiple of C, a rational multiple of C. And that's equivalent also to K squared being 0. And now for any elliptic pair, we can associate it with a minimal elliptic pair with a morphism, which is an isomorphism in the neighborhood of C. In particular, the order of the elliptic pair does not change. So the proof is just by running K plus C MMP. This works in any characteristic due to Tanaka and Fujino. And a technical remark here is that if you start with a minimal pair, elliptic pair such that the restriction of C to itself is not torsion, then by adjunction, combined with the fact that K has to be this rational multiple of C, gives in fact that K plus C has to be in fact linearly equivalent to 0. So in particular, K is a Cartier divisor, and under our assumptions, this implies that X has Duval singularities. So we'll also consider what we call a reduced restriction map. So remember, the restriction map was the map that was going from C perp into peak 0 of C. We take a divisor, we restrict to C. Now there is an induced map on C perp modulo the subgroup generated by K, because K times C is equal to 0. And so then the theorem is that if you have an elliptic pair with Duval singularities, if you take the minimal resolution, then the elliptic pair we started with is minimal if and only if its resolution is a minimal elliptic pair. And this is equivalent to, in fact, the Picard number of Z being 10. It's essentially a blowup of P2 at 9 points. In this case, this what I call CL0 of Z, this quotient, together with the intersection pairing on Z, we can prove this is in fact the lattice E8. And now here is our criterion for polyhedrality, and when the order of the elliptic pair is finite. So we need to assume that the pair is minimal, that the Picard number of Y is at least 3. So in this case, the effective cone of Y is polyhedral, if and only if the effective cone of Z is polyhedral, and if and only if the kernel of this reduced restriction map contains 8 linearly independent roots of our lattice E8. So roughly what this says is that there are many -2 classes, -2 curves in Z, and such that essentially we are able to write C as a combination of all these -2 classes, and this will somehow force us to have a face of a polyhedral cone. So to decide polyhedrality, and when the order is finite, we need a minimal elliptic pair and also Duval singularities. And so the upshot now is that if you start with any elliptic pair, you can consider it minimal model. If the order was infinite, then the effective cone is not polyhedral as long as the Picard number is at least 3. This is true for both X and Y. And in this case, Y actually is forced to have Duval singularities. But if the order is finite and Y has Duval singularities, then we get this polyhedrality criterion for the effective cone of Y. So in our case, we will start with a surface and the curve which are defined over Z. This is the blowup of our toric surface. By the definition of a good polygon, this will have infinite order when working over Q. Okay, then we look at the minimal model of X and to Y. So we contract the curves on which K plus C is negative. So now outside of finitely many primes, this will be contracting the same curves even when reducing modulo P. So the reduction modulo P of Y is still the minimal elliptic pair associated to the reduction of X. And so now, after reducing coefficient modulo P, the order will be finite. And now we want to study the effective cone of our YP, the minimal model of XP. And we want to study if its effective cone is polyhedral or not. And now this becomes very explicit in the examples. And so I just want to show you how explicit this is without going into the details. Yeah, so in the example I considered before of the polygon with the volume 36. Yeah, so here you contract 2 curves in order to get to the minimal model. Here is the minimal resolution. Here you take the minimal resolution of the toric surface, which is singular to start with. We can also arrive at our z by contracting -1 curves on the blow up of the minimal resolution. So this is the picture of how the curves that we contract relate to the minimal resolution. The two curves are actually proper transforms from one parameter subgroups. And then we are trying to find if there are enough -2 curves in the kernel of our reduced restriction map. And we notice that the sublattice of classes of -2 curves above the singularities of y are automatically contained in this kernel. So in the end, what it comes down to, for the effective cone of y to be not polyhedral in characteristic P, is that for our two generators P and Q of the Mortel-Weil group of our elliptic curve, in this case, yeah, so when we take their reductions modulo P, then these multiples of the reduction of P does not belong to the subgroup generated by the reduction of the point Q. And so we're trying to prove then that this condition, the primes for which these multiples do not belong to this subgroup, this has positive density. And this is an application of Chebotarev's density theorem and the theorem of Lang-Trotter. And it results in these primes under 2000 being the non-polyhedral primes for this particular example. And I think I want to finish here. Thank you for your attention.